So, let us generalize to reflection in 3D, but we take a cubic basis for simplicity, but it does not have to be cubic, it is totally general, it is independent of the coordinate basis and it is independent of the kind of symmetry operation you are having. So, let us do this. So, this is the x axis, this is the y axis. So, I want to write the reflection matrix, W representing reflection in xy plane. What we have to do? We have to find W A. Where will A reflect if it is reflected in the xy plane? Louder.
Not change, sir.
It will not change. This is what is called in invariant vectors. Some operations leave some of the directions or some of the vectors unchanged. So, reflection in the xy plane will leave A unchanged. So, W A is A in its the ABC coordinate system is 1 0 0, W B same remains B, B in its original coordinate system is 0 1 0, W C will do something interesting. What will it do?
0 0 1 bar.
Because if you are reflecting in the xy plane, instead of pointing up, it will point down and it will be a vector of the same length. So, W C is nothing but minus C. And minus C in our coordinate system is 0 0 minus 1. So, reflection W representing the reflection in xy plane will become transformed A, which is 1 0 0, transformed B, which is 0 1 0, and transformed C, which is 0 0 minus 1. So, this completely represents the reflection of any general vector, and you can see if you multiply it with any general vector x, y, z, what will it give you? This matrix yeah x, y, z bar. Now, if you are reflecting any vector in the x, y plane, this is what you expected, isn't it? It should not change its x coordinate, it should not change its y coordinate, and it should make the z coordinate negative. Okay. Now, this also shows an interesting. So, let us write rotation also, which is also simple. Now you have got the idea. I have cubic A, B and C, so they are equal in length, angle is 90 degree, and I am rotating by 90 degree about C, about Z axis, and of course I am forgetting to write CCW, so counterclockwise. So what is the matrix?
C will remain same.
C will remain same, very good. You are telling about the last column.
Yes.
So 0, 0, 1.
First will be 0, 1, 0.
Because the x axis goes into B, 0,
0,
1, 0,
and 1, 0, 0. No, sorry, minus 1, 0, 0.
minus 1, 0. Everyone is comfortable with that? Okay. Now let us establish some property, one property of the determinant of these matrices. What is the determinant of this rotation matrix? Hmm? It is 1. What is the determinant here of the reflection? Hmm? Minus 1. This difference in determinant is actually having a physical origin in terms of the handedness. What does reflection do to handedness? Handedness change. So, reflection will always reflect a right handed glove into a left handed glove, a right handed object into a left handed object. So, if a random matrix is thrown at you without telling that what it is, so if you determine it's just the sign of determinant, you can at least tell whether it changes handedness or not. If it's a negative, determinant is negative, there is a change in handedness. If determinant is positive, no change in handedness. Crystallographers use a jargon here, so let us get familiar with that. Operations which change handedness are called somehow, I do not know why they should be called improper, but they are called improper. There is nothing improper about them, they are called improper operations. Or sometimes type 2 operation. So, this is just the definition, that an operation which change handedness, that is whose determinant will be minus 1, is an improper operation or a type 2 operation. The one which do not change handedness is a type 1 or proper operation. So, means essentially we have introduced the classification. There are various kinds of classification. This is one classification of symmetry operation. type 1, type 2. Proper, improper. I don't like the word improper, but that's how it is. It's like your even and odd. There is nothing odd about the poor odd numbers. They're just number, but historically they are called odd numbers. So historically these are called improper operations. So the determinant will always be plus 1. This we have not proved, but if you reflect upon it, it will become clear that not only it will have a positive determinant, that positive value will always be plus 1 and determinant will be negative or minus 1. This is for symmetry operation. If it was not a symmetry operation, then also it can be a proper and improper operation, in which case determinant will be positive, but different from 1, and negative, but different from 1. But if it is symmetry operation, it has to be plus 1 or minus 1. This is an application of what we learned when we were talking about the determinant in connection with coordinate transformation. So, where we said the determinant of a coordinate transformation matrix, that determinant of Q determinant Q was V old by V new. Exactly the same argument is there for determinant of W also. Is V old by V new.
So should it be like V original by V?
Yeah, you can call it if you want. Old is original, V original, and new is the image of the original or transformed original. So, you can call it V image. But in the last class, we saw that symmetry transformation is an isometry. What does that mean?
The length.
Not change dimension.
Symmetry transformation is an example of an isometry. So, lengths and angles do not change. If lengths and angles do not change, then what can you say about the old volume and the new volume?
The amplitude don't change.
Sorry?
The amplitude of the volume will not change.
Amplitude or the magnitude of the volume will not change, because all lengths are the same, all angles are the same. So, volume of the unit cell box cannot change, only unit cell box or the unit cell parallelepiped is being transformed in space. If you are rotating it, it was here, now it has got rotated there. If you are reflecting it, it was here and it has got reflected there. But since its edge lengths cannot change, and since the angles between its edge lengths do not change, so even if you think in terms of that vector formula A dot B cross C, the triple product, the volume is not going to change. So, isometry so V old has to be equal to V new. only as we saw that if it is reflection, the volume is having a negative sign. Okay. If it is a reflection, the new volume will have a negative sign. So, it will be either plus or minus, because determinant is changing, because a right handed system changes into left handed system. So, A dot B cross C, if it is positive for a right handed system, it will become a negative for left handed system. So, that clearly shows us that determinant W, if it is a symmetry operation, has to be plus minus 1. So, this is an interesting result and we have to keep in mind. It is also a check, it is also a check whether you, after you have written your symmetry operation, whether you have not made any numerical mistake or so. So, if you calculate the determinant, if it comes any different from either plus 1 or minus 1, whatever it may be, it is not a symmetry operation.